Hi everybody, this is Matt Ingram with a replication of Corey Sparks' piece from 2011. This replication will be in R. A couple of preliminaries. I assume you have downloaded and installed R at this point in the course. This should not be a hurdle. You should also have all relevant packages installed. We'll go over this in detail, but the main extra package for this replication is R2 Windbugs. I also expect you've downloaded and installed Windbugs. You can do a Google search and find out how to do that. I also have a separate video on that. And if you're working on a Mac, since Windbugs is designed for a Windows machine, I assume you have downloaded and installed either a Windows emulator or interface that translates individual programs or commands from Windows to a Mac or Linux environment. One of the best options for that is Wine, which stands for Wine is not an emulator. Again, you can do a quick Google search for that and download it. If you're not using an emulator or this kind of interface, I assume that you're working on a Windows machine on campus or at home with R and Windbugs installed as noted above. So the steps we'll go through from the article, I assume you've read the article and digested it. Its theoretical motivation and the substantive research problem. So we're going to generate the summary statistics in Table 1, the model results in Table 2, and then the visualization of the core results in Figure 1. That's the three maps or panels with the predicted risk at different thresholds. We can then go through different extensions. I've added data from the 10 city council districts in San Antonio, and we can estimate two models, one with just varying intercepts for the districts at this higher level of analysis, and then another one with a single covariate at that district level of analysis that I've called runoff, and that's whether a runoff election was required in the 2003 election for the city councilor in each district. So let's get to the paper and to the R code. The paper, again, is this paper by Corey Sparks, 2011 edition of Spatial and Spatial Temporal Epidemiology about violent crime in San Antonio. The dataset contains data on violent crime and property crime. The focus here is on violent crime, so that's what we'll do. And basically we want to replicate the basic results. So we want to be able to generate these descriptive statistics in Table 1 up at the top, and then the core results are the ones down here in Table 2 at the bottom, and then we want to be able to generate these maps on page 3 at the top of page 306. The predicted risk at increasingly higher thresholds, 1.5, 2, and 3. So let's get to the first part of the replication and just get into R and start working with this. So if we pull up R, we see our familiar environment here with the console in the top left, and I've got the R code open here, the R script open here. If you're working in RStudio, everything should be the same. All the content should be the same, just your setup might be a little bit different. So go through, you've got some basic introductory materials here. One person that I should definitely thank individually, we'll add them here in the next script, is Johannes Kareth here in our own department. He's just been incredibly generous over the last week, helping to troubleshoot some of the code and get the analysis set up. So thank you, Johannes, Professor Kareth. So the first step is to load and install all your packages here. Just start with Windbugs here. Later we'll talk about using OpenBugs. But start with Windbugs and this second package, EpiCalc. I've already installed them and opened them here, so I won't do that now. Make sure you require them or open the library as well. Then you can skip down those. We won't need some of the additional packages yet. Make sure you set your directory. You can see that it calls a directory up here on the left. You can skip this block here, and then as I alert you, use this block down here to load your shapefiles. So in the directory you have the shapefiles. The paper data v2 is the primary shapefile with all of the data in it. And then we have a line file with the outline for the city of San Antonio, and then another file with the outline of Bexar County. So we can load all of these. For the extensions, you can add this new data on districts. You can skip it right now if you don't want to work with the extension just yet. But if you add all of this data here, using Control R to execute that code, you can then plot the districts, the city council districts in San Antonio, and you can see that visualized here in the plot. These aren't exact. I've had to approximate a couple, so I wouldn't rely on these for any future publications. You want to do a finer job, but this is approximately correct for 2003. We can then extract some additional data that I've collected on a 2003 election. With that block there, we basically created two variables, whether a runoff was required, and then the margin of victory in 2003. We can add both runoff and margin of victory to our shapefile, and our shapefile should now contain both a district ID and then this data on runoff and margin of victory. We can extract the data frame from our shapefile with that command, and then we can skip down unless you want to examine some of these variables. Let's skip down. You can plot some of them with all of this code here. You can familiarize yourself with the dependent variables, violent crime and property crime. There's some more plot commands. Here are some transformations that the author did to generate some mean-centered scaled versions of the variables. We don't need to do that here since it's already been done, but you can repeat it and play with this code if you like. I've added some additional code if you want to write out a shapefile or add a projection component. We don't need to do that either. But now we can come down and examine the descriptive statistics for all of our independent variables. So you could run this block here. You'd want to run them individually to extract the histograms of the codes. Or you could also create a summary of the data file or of DAT and look at each one of these variables. So if you did this, you could look through and find each of the independent variables. We're not going to reconstruct the whole table with the descriptive statistics, but you could summarize each one of these variables or look through them in the full report. Look for them in the full report here. For instance, this is let's find the first one, ZABC. Here it is. So this is ZABC. This is the alcohol and beverage establishment, a minimum of minus 0.19, a maximum of 13. If you go back to the paper, you can see that there's well, he reports averages and standard deviations. So the average is 0. Well, these are actually not the normalized ones, so you'd want to go back to the raw scores, excuse me. So those raw scores are up in the data. You could find them. Again, we're not going to do this for every single one. You could also write some code to extract each one of these variables and place them into an object that would look like that the table of descriptive statistics. Let's skip that for now. Except let's just pull out one. So let's just summarize data, and I believe it's just called ABC. So there we have it, a mean of 4.6, and you could calculate the standard deviation here, or you could also simply extract it with data. It might just be SD. The mean 4.6. Let's see what the paper does. 4.6 and 24.29, and what we have is 4.6 and 24.29. So you could go through this and extract the mean. If you didn't want to do the full summary, you could just extract mean of data ABC. You could execute both of these commands right here and extract the mean and the standard deviation for each one of the variables in table 1. So that's table 1. I'll leave the rest of the variables up to you. What is of greater interest to us is table 2. The code I have here in R is for model 2, but you can see how you could adjust the code to generate model 1. So below the parts that we've just been seeing in the histogram, there's several plots here. You can plot out all of the independent variables. You can also plot out runoff and margin of victory with P10 and P11. Those are these graphs here. So those are all ways of exploring the data. This code here generates your spatial weights, so we'll execute that. And then you can generate a simple linear model of the data here. So you could use this as a base model to compare the final results in model 1, model 2. Skip this next block because it's old code, or it's old syntax. But in this block here, you could also fit other models, including a simple spatial lag model here. This one might also be interesting for you to execute, again, for comparison's sake, to compare the eventual models. This is where the interesting part of the code, or the really new part of the code, starts with the Windbugs. Again, we're going to be replicating model 2, but for model 1, simply drop V and any related elements from the code below. So first we want to generate n, or the number of observations. That's the length of one of our key variables. Next we want to start some initial values that the Bayesian analysis is going to use to conduct some of its estimations. You can see some explanations in comments above here, but we're going to just move quickly through this, and then we can talk through it more in class. So just generate your initial values. Make sure that the initial values in here, in zeros, in between the parentheses, match the number of parameters, or the number of coefficients that the number of independent variables that you're going to be exploring. And then we want to tell Windbugs where the data is in terms of D. So we have our dependent variable and then all of our independent variables, and then down here you have the spatial weights information extracted from the spatial weights matrix which we generated above. Next you want to set a folder for the output from the Bayesian analysis that Bugs will conduct. You want this to be a short file path and not to have any spaces, as the comments indicate above. So I made this just a short path to my Dropbox folder and created a new folder. And then here is the model. It goes from model 1, left arrow, and then the open quote, all the way down to the quote closes down here. So just make sure that you grab all of that that entire block of code from model 1, left arrow, open quote, until the quote closes. We can execute this. You see it executed on the left. And basically what we've got here is the very simple model specification. This is a Poisson distribution. The D stands for distribution. And this is the simplest, most general abstract form of our model. Then we want to tell Windbugs what each one of these elements means. So mu indexed at I, or mu sub I, is then defined in this next line here as a function of theta sub I and the expected value. And then we define theta sub I here. This is what you would generally think of as your more fully specified model with all of your independent variables. And U is the unstructured error component, And then V is the spatially structured random effects component. This is, sorry, this should be random effect. This is what in the paper Corey Sparks calls sigma sub E here. This is the, sorry, sigma sub S is the spatially structured component. So in the code again, if you wanted to generate model 1, you would simply drop V and all other references to V throughout the model. So then you want to give your prior distributions for all of these components, and V here you see that it's distributed with a conditionally autoregressive. It has a conditional autoregressive distribution with our weights, spatial weights information here. Again, we have all of our distributions down here, and then down towards the bottom, for each one of our betas, we want to sample from a normal distribution. So we've already specified this model. We'll talk about it more in person, but that's a brief overview of the model. Then you need this block writes out your model to your bugs folder. You see it back here, you've got your data in text format, your initial values in 2 text formats, and now you can do the estimation. This is the actual estimation. Some of the lines are commented out for future reference. So you see down here, if you're using Openbugs, I've commented that out because I'm not using Openbugs. One thing to keep in mind before you execute this, just make sure that the number of iterations is small, maybe 10 or 100, and then you want to burn in some initial iterations that will be discarded, and you want that to be, you know, the notes for Windbugs say at least 2. You'll get an error if it's less than 2, but maybe approximately half of what your total number of iterations is. But make it a very small number, 10 or 100 at first when you first run this, just to make sure that it runs. In one run of this, I specified 100,000 iterations, and that took about 25 minutes, 30 minutes on my machine. So let's run this here, and you'll see Windbugs called, and then it proceeds through the analysis and generates some results. These results will not be very good because we just have 100 iterations, but essentially what you want to look for is convergence in these 2 lines. These are your 2 initial values, and if it's performing well, these 2 lines will eventually converge like they do here, but eventually explore the same space and the same range of space, and they'll do that in what Professor Kareth calls a fuzzy caterpillar kind of form. So that's one automatic output that Windbugs generates, but some nicer diagnostics are offered below here under Diagnostics. But first, you could just print the object that we just created with the bugs command, and that's up here. What you're most interested is up towards the top. You'll see 235 observations for U, V, the spatially structured random error, theta, which is essentially our predicted outcome, and then you see here alpha, the intercept, and 9 coefficients. Right? So here you see the mean, the standard deviation. You could just report the mean and standard deviation in your results table, but you could also take the 95% credible interval from the 2.5% limit to the 97.5 limit. And essentially, using that data, you could replicate table 2 here. You'll see the intercept here. Sparks has reported should be the mean, and then the boundaries of the 95% credible interval. So that would be the mean here, and then these would be the 2 limits, 2.5% and at 97.5% would be the outer bounds of the 95% credible interval. Again, you could just take the mean and the standard deviation. These values will not match up, or probably might not even be very close to Spark's values, simply because we've only run 100 iterations. So you'd probably want to run many, many more, maybe 10,000 or more, in order to get those nice, smooth patterns. We can talk about that more in class, but just make sure this runs initially with a very small number of iterations, maybe 10 here and 5 here. Just make sure you get familiar with the program. Go back and digest what each of the elements might be. You could read the help files, but we'll talk about it more in class with a model that has been run with 100,000 iterations. Again, the diagnostics are particularly useful if you plot the object. You'll get a very simple output that looks like this. Here are your betas, your coefficients, 1 through 9 in respect to 0. Again, to interpret significance, you want the 95. These are 80% confidence intervals, or credible intervals rather. So you want 0 to not be included in that interval. Here's your predicted outcomes, the spatially structured random effect, and then the unstructured error term. Prettier, you could say, plots are offered with MC plot. You want to load that with these two commands, install packages and library, but then with MC plot, I need to call it first, if that would be helpful. You'll see that you get some much more elegant or aesthetically pleasing plots that will help you diagnose the performance of your model. And then the code below offers various options for plotting dot plots and doing some other diagnostics. So I encourage you to play with these other diagnostic tools on this basic replication of the results. And then lastly, as soon as this other diagnostic plot is done executing, it just finished here. So these are the more elegant, aesthetically pleasing plots. Essentially what you want to see is that your two initial values, take for example these two, this is for the intercept for alpha. You want to see the two initial values converge, so they should be plotting something that looks like a bell-shaped curve, and that the blue and the red plots are plotting about the same space. You want to see this bottom long plot again doing something that looks like a fuzzy caterpillar, essentially, where they're overlapping each other and bouncing up and down and covering the same space. We'll see what that looks like in class. And then down below, the ones that you'll eventually be more interested in are the plots for your betas, for your coefficients. Right? So this is beta 1. This is your first coefficient. That was alcohol and beverage establishments. Beta 2, land use diversity. And we can scroll down and see the rest of them. Again, none of these are significant simply because we have so few, or none of these are worth interpreting right now since we have only 100 iterations. But here you see with theta the kind of pattern that you might be looking for. This is our predicted value, just the very first one. You can see that these two lines are overlapping each other, and here you see the kind of pattern that approximates what you want to be looking for, although eventually you'd want to be looking for something that's bouncing up and down at a much more frequent, rapid rate. But this begins to look like what you might be looking for. And the other thetas. Ultimately, you'd want to run far more iterations of this in order to be able to do any kind of interpretation. So we'll stop there. In the returning to our R script, you could do some dot plots to do some interpretations, especially if you choose to run more iterations in your model and you feel like you're reasonably confident in the results. I'd run at least 10,000 iterations with maybe 5,000 burn-in, and just be prepared to wait depending on what kind of machine you have. But once you do these dot plots, you can extract the mean of the spatially structured random error, the mean of the unstructured error, and the mean of your predicted outcomes. Excuse me. Then you can also plot these, right? So we could plot the predicted outcomes, and that's what this would look like. But if we wanted to get to our plots in figure 2, we would come down here to these risk ratios. So the best kind of graphs are these. If we do P1 through P2 and P3, just execute that, and then if we tile them horizontally, they will look like this. And again, what we're trying to do is replicate figure 2 on page 306 in the article. Oh, so excuse me, that's figure 1 on page 306 in the article. And if we maximize this, this is essentially what those 3 panels look like. So we've just replicated figure 1 in the article, which is the visualization of the core results. So hopefully this is enough to get you started and playing with this data, and I look forward to our discussion and further extensions of it in class. Thank you.